So hey everybody, my name is Jerry. I'm the co-founder and CEO of LlamaIndex, a popular open source framework to build LLM applications over your data. And today I think the topic that I want to discuss is just like, it's practical data considerations for building production-ready LLM applications. So kind of moving a little bit beyond some of the super simple stuff into kind of like some of the more advanced stuff. Okay, how many of you guys are familiar with Retrieval Augmented Generation as a term? Okay, so let's start from the basics. Let's say you want to build an LLM application over your data. This is typically the stack you do to build an LLM kind of like system and like build like a QA system using a large language model over your private data. So you start off with some like source documents. You want to chunk up these source documents into a set of like text chunks and then put it in like a vector database, like a Pinecone, Chroma, Weaviate, Milvus. And then once it's actually stored in the vector database, you have like a query stage where you do some sort of like retrieval and then querying on top of this data. And so basically you retrieve this data from the vector database and then you feed the chunks into the language model as part of this thing called like in-context learning so that you can actually synthesize a response using the language model. So this I call like the naive RAG stack for building a QA system, because this is like probably the most basic thing you can do. If you do this with like LlamaIndex or LangChain, you can basically do this on like 10 lines of code, right? It's pretty basic. So kind of going into this a little bit more, the naive state of like data ingestion and parsing is that you split up documents into a set of like even chunks. The chunk itself is just like a text block, right? It could be split by sentences, characters, those things. And then all these chunks are stored in the same collection in a vector database. And then during query time, you use embedding similarity to find the top K most similar chunks from the vector database collection, and then you plug it into your LLM, like do response synthesis over the data to get back an answer. Okay, so if you've ever built this type of system before, you know that like a lot of times it doesn't actually give you the best response. And when retrieval augmented generation fails, the most common reason is that the retrieval system is bad. So if the retrieve results are bad, like even if you have like GPT like 20, there's no way the LLM can synthesize like a proper response without like hallucinating some sort of information, because it doesn't know anything about the retrieved data because your retrieval system didn't actually give back the right data. And so the most common retrieval method these days is like top K embedding lookup. There's some causes of bad retrieval quality. Each chunk that you split from the source document does not have awareness of the parent context or related context. The query itself might be kind of complicated, and it might assume like you need to kind of traverse your documents in a certain way that like top K embedding lookup doesn't actually do. And then the data might also, you know, if you have multiple versions of the data, it might be like redundant or out of date. There's also like practical system level considerations with this stack, because like this basic thing is pretty easy to set up for like a hackathon project. But then like, let's say you want to deal with like updates in the source document. How do you actually propagate updates from your source document into your vector database or into any other data collection that you store in terms of like the chunks that you store in the database? How do you adjust like chunk size over a large corpus of data? So there's a lot of like system considerations if you're trying to actually productionize one of these LLM-powered applications. So one of the key lessons here is that if you want to improve your retrieval augmented generation stack using LLMs, you want to improve the way you handle state and not just the retrieval algorithm. And that's kind of like the purpose of the talk today. And really just like the higher order bit is just like, if you want to build an LLM system over your data, you kind of need to take into account all these considerations if you're going to build a production quality application. The first point is augmenting chunks with context. So one of the reasons like embedding-based retrieval fails is that like the relevant context chunks don't actually like match the query embedding, because they lack like global context about the kind of like about like what the entire document is about. So one thing that you can do is actually inject metadata into each text chunk. Imagine like the GPT-4 like archive paper. You split it up into a bunch of text chunks. But then, you know, like maybe for each one, you append metadata, for instance, like the page number, the organization, those things. And then you inject this metadata into the text chunk. Now when you actually do retrieval over the system, the embedding-based lookup can utilize the fact that there's metadata, you know, in these text chunks to actually kind of do similarity lookup and pull relevant information. The other bit is it's nice to kind of actually explicitly define node relationships within your data. So if you have like a text chunk right here, it might be good to define, hey, this thing happened after this thing, and this thing actually happened before this other thing. And then this thing is actually a subcomponent of this overall thing. And by defining the state, you can actually design like a better retrieval system over your data, so then the LLM has enough context to kind of not just exploit the current information, but also exploit relationships within your data, so that it has more information in general when it actually tries to synthesize a response. Here's a very simple use case, right? Let's say we're kind of asking, this is like a question over, I think, a Uber like SEC filing, like what was the impact of COVID, and show the statements in bullet form, and then also show page numbers. Obviously, if you just split the text by itself, each chunk is not gonna have knowledge of what the page numbers are. But if you actually just add page numbers as metadata to each of these documents, you can actually get kind of like, you basically inject the metadata as like a annotation, like page label 6, page label 18. Then when you actually create this overall system, you can ask these questions where it can actually cite the page numbers given the context. Cool. That's just one of the steps. I actually don't have too much time, so I'm just gonna kind of go through the higher order idea of a lot of these things. The other thing is just like pick a good parser. Sometimes there's a lot of like these different types of text splitting strategies when you break down a document into a bunch of chunks. There's character splitting, there's token splitting, there's sentence splitting. There's a lot of like out-of-the-box file parsers. There's a company called like Unstructured that builds like really nice kind of in-house native parsers over different file formats. But like for certain use cases, you might have to inevitably write your own parser. So for like an SEC document versus like a Supreme Court filing versus like an Instacart web page, these are very different kind of data representations, and you're probably gonna in the end have to do something custom for each one of these. The next piece is like being able to define the right indexes over your data. So can you tell me about like Google's R&D initiatives from 2020 to 2023? I guess like the higher order idea here is that putting all the chunks into a single collection and not separating the documents in some way will probably lead to pretty bad results. Because if you ask this question, and you ask a question like this, and you say like fetch the top 4 most similar chunks from the vector database, you're not really guaranteed to get back specifically, hey, the R&D initiatives year over year, right? You're probably gonna get back like a bunch of random chunks. Some of them might be 2020, some of them might skip a year entirely, some of them might be like 2023. And so the idea here is that like by defining some sort of structure over the way you actually store the data, you can actually inform the retrieval and actually get outputs in a more structured manner, right? And so if this is getting a bit technical, the key idea is like you kind of have to think about this when you're actually building this like overall question answering system of your data, right? It's not just like as simple as, okay, I'm just gonna throw a bunch of stuff in a vector database, ask a question, and it's gonna magically work, right? These are all things you kind of have to think about. The last thing I'll probably talk about is if the source document changes, you kind of need a way to like update the nodes in the vector database. For instance, like let's say this document is like a web page and there's like an edit attached to it. Or this is like a patient history and all of a sudden it gets updated with new information. You can choose to do some sort of batch update. You can choose to do some sort of like rolling, like a trigger-based or real-time update. But ideally, every time you do this, hopefully you don't need to re-update the entire collection. So if you go from a source document to your vector database, you probably need to have some mechanism to like sync just the relevant changes. So this is, again, a bit technical, but like if you just maintain a hash for each document and kind of like hash the context, and then you maintain a mapping from like the node doc ID to the source doc ID, if the document hash changes, you can basically kind of say, hey, I know this document has changed, please update all the nodes in the document ID with the same document ID with the new content, right, and try to re-embed everything. So that's basically kind of like, these are all the problems that LlamaIndex tries to solve, right? And so we try to do not just like the simple stuff, which by the way, if you try this out, you can like do the simple stuff in like 3 lines of code. We try to really think about the advanced stuff too. And so these are all kind of like data considerations that you kind of have to think about if you want to build a production-ready LLM system. Cool. I think we're going time.
If that's okay. All right, questions?
Hi, so just for the example of the Instacart webpage, let's say I have description of, okay, let's say you go to an Instacart webpage for like vegetable juice, for example.
Yep.
If you have like a description of the vegetable juice and the nutrition facts, what is the thought process? Because question answering is a typical NLP task. So how would you think about whether to just use some question answering model like as you would treat a regular NLP question answering task versus using this RAG stack?
I see. Are you, I guess like, I guess one bit of this is like, should you use like a language model, right? Like
Yeah.
the idea of like a large language model is that it has some sort of like big context window that you can try to like put stuff in there,
Yeah.
right? The other option, of course, is like, I guess part of what you're getting at might be you can try to like tune the model itself so that like the model itself can internalize a bunch of information. I think these days with large language models, probably the more popular approach is really just like using the model as is, and then actually trying to like fill in the input prompt with a bunch of context. And I think part of this is like creating like a good data pipeline so that you could actually fill the prompt with the right context, given that the model is fixed. Yeah, but I think, yeah. Yeah. Oh, I would actually argue if there's not, so the question is like if there's not that much data, is there value in kind of using a large language model? I'd actually argue, yeah, I think if there's not that much data, it actually, then you can kind of like exploit the fact that there's like this input prompt space that you could put stuff into, right? Basically, you just like use the input as like this cache space so that it can just like internalize and reason over new information. Yeah.
We have another one in the back.
Yeah.
So I have a question. So I want to confirm, basically you're using those contexts as a metadata for filtered query, right? To improve the search relevance of the answers being returned. So how do you determine what context should be indexed as metadata in your system? Because for so many different type of data sources, there are so many different ways for you to define the metadata. So I think that might be a challenge.
Yeah, so that's actually a great question. I honestly don't have a great answer to that. I guess part of the point of this talk was also just like, you should think about it and it should probably be domain specific. And so like if I've talked to like a few kind of customers building different types of applications. So if you're building like a legal chatbot versus like building a e-commerce like shopper, the type of data and the type of metadata you're gonna have to inject is generally going to be different. I could imagine like, as the months go on, there will probably be some sort of like best practices for like, for like PDFs, you generally should put like page numbers in the title and that type of stuff in there. But I think right now it is very like data specific, right? Like PDFs, page numbers definitely, the title definitely, but like other stuff, like it's probably a little bit specific to the case, the kind of like problem statement that you're trying to solve. Yeah.
Thank you.
All right, thank you so much. Please give a big applause.
Cool, thank you.
Thank you.